Hello, everyone. I'd like to welcome you to week 2 of our Thermodynamics class highlights. You'll recall that in week 1, we looked at reversibility and irreversibility. For week 2, we are looking at first law of thermodynamics. There are many statements of the first law of thermodynamics, but this one out of them all is one of my favorites. The statement of the first law of thermodynamics: although energy assumes many forms, the total quantity of energy is constant. And when energy disappears in one form, it appears simultaneously in other forms. This means that energy is conserved. So the total amount of energy remains the same. You can't create and you can't destroy. Please note that in this discussion, we are not going as far as nuclear reactions. So energy can change form and can move from place to place and can change from one form to another. But the total amount of energy is conserved. For us to apply the second law to chemical engineering processes and other processes for that matter, the sphere of application are the system and surroundings. The system is our region of interest, while the surroundings are made up of every other thing outside the system. And usually the system is bounded by a boundary separating it from the surroundings. And so the energy we talked about in the first law can move from the system to the surroundings, from the surroundings to the system. So equation 1 gives us the basic understanding. The total energy in the system will change, that's delta E. And the total energy in the surroundings will also change once there is a change of energy in the total energy of the system. So equation 1 says that this change in the system and the change in the surroundings cancel out. So it means that whatever change in energy occurs in the system, a complete reversal of it will occur in the surroundings. For the surroundings, we are not interested in the various forms the energy assumes, but for the system, we are. So the change of energy in the surroundings will assign heat and work. Heat and work are energy in transit. But the forms of energy that reside within a system are given in equation 3: internal energy, potential energy, and kinetic energy. You are used to potential and kinetic energy. So the potential energy is the energy possessed by the entire system on a macroscopic scale as a result of its position. The kinetic energy is the energy possessed by the system on a macroscopic scale as a result of its motion. But internal energy is the energy possessed by the system on a microscopic scale, both potential and kinetic. You know, the molecules are in motion, That's kinetic, and there are intermolecular forces too that give it the potential component. But they all, at the microscopic or molecular level, make up the internal energy. So all these forms of energy constitute the energy in the system. Now the surrounding is so large, it is the rest of the universe. So we won't go and be checking the changes in all over the universe. So we will just use what comes into the system or goes out of the system to know the change in the universe. And that will be transit. Energy in transit takes only two forms, which is heat and work. This means you don't store heat in a system. You store internal kinetic and potential energy. A system can possess that. But when this energy forms they move as heat and work. If you look at my equation 2, I have plus and minus there. The sign convention we will discuss shortly. Okay, so the choice of sign plus or minus depends on the direction of energy transport. So energy motion is heat or work. And the direction, whether it is flowing from the system to the surroundings or from the surroundings to the system, that determines the sign. Before we conclude on that, let's look at two systems. Open and closed systems. Figure A. Sometimes I like this hand-drawn things because it puts a touch of nature to our class, so that all things will not just be artificial. Yeah. So figure A is an open system. An open system means that this is the boundary. The system can exchange matter or material with the surroundings. Thus, N can flow in and out. This means that this boundary is permeable. The system can exchange heat and work. This is heat, can flow in or out. So this boundary is diathermal. The system can exchange work. That means it can do work on the surroundings, and the surroundings can do work on the system. So the boundary is movable. A closed system is impermeable. So it only allows, the boundary only allows for exchange of energy. And we have said energy can be exchanged between the system and the surroundings in two forms, either heat or work. So we're dealing with a closed system here. And so equation 4 tells us that all the changes of energy, for the first law, we're just concerned with energy. So this is for a closed system. All the changes of energy on the left-hand side of equation 4 will be equal to the heat that flowed in or out and the work that flowed in or out of the system. Now the sign convention. By convention, under the International Union of Pure and Applied Chemistry, transport across the boundary from the surroundings into the system makes the quantities positive. Otherwise, they are negative. Hence, if we look at what is coming into the system, our equation 4 will translate to 5. We will just pick the positive signs and have the right-hand side as Q plus W. But in reality and in practice, it is the work done by a system that we're interested in. And so in most textbooks, you will see the right-hand side of equation 5 written as Q minus W instead of Q plus W. This implies that Q is heat added to the system, and W is the work done by the system, since the system is the object of our interest. Equation 5, right-hand side says that heat is added to the system and work is added to the system. So it means work is done to the system. But equation 6 says heat is added to the system and the amount of work done by the system is W. This will help your calculations to be accurate, because once you miss this sign, depending on the scenario you're addressing, you might just have issues with writing plus, then minus, or minus minus. And once the sign changes, your calculated results will not be correct. So we can conclude that the first law is applicable to the system and its surroundings with the sign convention that ensures accuracy during calculations. Thank you very much and see you in the next video.